So I think we were just in the middle of deriving the variational Euler-Lagrange equations from the action, gravitational action. So in other words, deriving the Einstein equations from the gravitational action. So I might as well just carry on with that. Let's put this. So remember we had started with the gravitational action, which you can imagine as defined for some bounded region of space-time if you want it to be finite, or even the space-time as a whole if you don't care about the fact that it's actually a divergent integral in that case. But when we come to take the variation, let's see, have I said that yet? I guess when we come to take the variation, we'll imagine it as if the action was the space-time as a whole, and we make only a variation of compact support. In other words, we make the variation only in a bounded region, so that any surface terms that come from an integration by parts can be neglected. That's always the usual rule in deriving variational equations. Like when we did for the particle, we fixed the endpoints, but it's enough. It would have been also just as good to say that we didn't have any endpoints, but we limited the variation to some restricted region. And as long as the endpoints were out, if there were endpoints were outside of that region, it wouldn't make any difference. In this case, we have not just a world line, but of course we have a whole field on space-time, but the same idea will apply. We'll make, in deriving the equations of motion, you assume that the field values on any boundaries that may be present are held fixed, and that's equivalent to just saying that you imagine no boundary and you make a local variation. Okay, so anyway, we'll see where that comes in, but that's the background. And then there were two terms in the gravitational action, one of which is the so-called Einstein-Hilbert action. I think that's what this is called. And then the other term was just a constant, dV, right? Where V, okay. Where dV, I remind you, is in a particular coordinate chart, takes this form. And I think I mentioned last time that it takes this form even without any reference to a coordinate chart. But if you want to think of this without a reference to a coordinate chart, then you have to understand exactly what is meant by the determinant of G and what is meant by this in a way that's intrinsic to the manifold. And we didn't actually do that yet. So for present purposes, you either just think of this as one undivided object. This is just the volume of a small region, infinitesimal in the limit, in which you're summing over and doing the integral. But in a coordinate chart, it takes this form. And so there, let's see if I can. So there are two. So for now, I'll not prejudice whether there's a boundary or not. So I'll just write this. This might be a bounded region, or it might be the whole of the manifold. In anything we'll do today, since we won't be worrying about the surface terms, you might as well take this to be the whole manifold. But for future reference, maximum generality, I'll keep it as an arbitrary region. Okay, so this action has in it two free coupling constants. The gravitational constant, also I'll remind you that kappa is equal to 8 pi times the Newton's constant. C is 1 as always. So there's two coupling constants, as you might call them, free parameters in the action, one of which is this, and the other one is this cosmological constant. So now so in varying this, we have to vary two terms. Each one involves a variation. I mean, this second term is no more than the volume this integral of lambda dv, of course, that's just the volume of the region kappa, x, whatever this is, times lambda. So varying that is just varying the volume. And varying this is more complicated. We have to vary the Ricci scalar as well as varying the volume. But in both of them, we have to vary the volume element. So let's start with that. So there's several steps here that are sort of come up in many contexts over and over again. So it's good to understand each of them. And they've all been the formalism has been arranged so that these steps can be done clearly and simply. I don't know, when people first had to do this, I don't know what they actually did. Maybe they just wrote this out as a whole bunch of second derivatives of the metric. I don't know actually how, but now there's a sort of machinery developed to smooth these calculations. So, of course, we'll use that, including the definition of the Christoffel symbol, of the connection, the Christoffel symbols. I think they didn't even, as far as I know, the Christoffel symbols, that is the notion of covariant derivative, wasn't actually even defined when the theory was first written down. So there's, I think if you look in Riemann's paper where he introduces the Riemann tensor, he doesn't, I'm not sure if he calls it the Riemann tensor, but he introduces it, its components anyway. But there's no mention of the connection. I think that actually came later. So he just derived it directly as some sort of covariant object associated with the metric. So for this, I'm just going to quote the answer. Mainly just going to quote the answer. And we'll come back and then justify it later. So the answer is the following. So this comes up over and over again. This comes up even in flat space, because if you're trying to define this energy momentum stress tensor of a field in flat space, the simplest way to do it is to imagine that you were in curved space and vary the metric, and that'll give you, and so whenever you do that, you have to vary this volume element, but I left out the dv. So the variation of dv is just equal to dv itself times 1/2 GAB times the variation of GAB. Okay, so that's the first intermediate formula, which is useful. And you can actually remember everything is sort of here. You can sort of remember why it has to be there. The variation of the volume, if you vary the metric, like if you would just double every length, for example, that would be varying the metric. So the change in the volume will be proportional to the volume itself, of course. So that has to be here. And then you need the variation in the metric. You need to get a scalar, so you need to contract it with the metric. The only thing that's not obvious is perhaps the sign. But if you think about it, making the metric, if you make the metric bigger, then obviously you make volumes bigger, so you ought to see a plus sign here. And then the 1/2. But the 1/2 you can actually remember if you think of as a sort of general rule that very often works, which is when you contract two symmetric tensors, you introduce a 1/n factorial, where n is the number of totally symmetric or totally anti-symmetric indices. Anyway, that's all. So in this case, 2. So it's 1 over, you can think of this as 1/2 factorial. Anyway, or you can think of the 1/2 as coming from the square root in the square root of g. Anyway, those are all just memory devices. So anyway, we have this formula. We'll use that, and we'll come back, hopefully very soon, to show how you can derive it in a coordinate chart from this. Okay. So now the hard part of the calculation is to find the variation of the Ricci scalar. But the Ricci scalar, remember, was defined just as by contracting the Ricci tensor with the metric. And that's, of course, And we got the Ricci tensor by taking the Riemann tensor. And contracting its only contravariant index with some partly randomly chosen covariant index. Okay, so those are the definitions. So if we're going to vary the Ricci tensor, we have to know how to vary the metric, and the inverse metric in this case. And there's a rule for that. And then we have to know how to vary the Riemann tensor. So let's start with the Riemann tensor. So to see what the variation of the Riemann tensor is, it's easiest to go back or it's natural to go back to the definition of the Riemann tensor and just vary the definition. But let me mention first something. So remember, in the definition of the Riemann tensor, it just measured the non-commutativity of the covariant derivatives. So it's basically the commutator of the covariant derivative. So if we want to vary the Riemann tensor, we want to know how to vary the covariant derivative. So what does that mean? So if we imagine the covariant derivative applied to some vector, then from that, of course, you can get everything else. And we can think of that, we're not varying the vector, we're just varying the metric, and therefore the covariant derivative. So if the variation of the vector is 0, then we just have what you might call the variation of the covariant derivative itself times the multiplying the vector. But remember, this variation of the covariant derivative means to take the difference between the old covariant derivative and the new covariant derivative. But if you remember when we discussed the covariant derivatives, one of the main things we proved is that the difference of any two covariant derivatives is expressed by a tensor that has the same index structure as the Christoffel symbol, and that you can actually think of as the variation of the Christoffel symbol. So I'll write it in that way. Okay. So remember I had called this, I think I had given this a name of like CBCA. This is infinitesimal, of course, in this case. It's the tensor that relates the two covariant derivatives to each other. So in other words, C, you can think of it as being the difference of the covariant derivative belonging to the perturbed metric minus the covariant derivative belonging to the metric unperturbed. So by this square brackets, I'm kind of indicating it's a function. It's a differential function of the metric. Okay. So anyway, that's the meaning of the C, which I've called it delta gamma instead. So why have I called it delta gamma? Because if you were to work in a coordinate chart, it would be delta gamma. So there's no need to have a separate symbol for it, as long as you remember that this delta gamma is truly a tensor, unlike gamma itself, which depends on the coordinate system. This delta gamma, which is C, really is independent of the coordinate. But for notational simplicity, I'll just call it, instead of introducing a new symbol, I'll call it delta gamma. And we know it's a tensor. So the key thing is that this is a tensor. Okay. Now let's plug this definition in to the definition, the equation that defines, do I have A and B? Yes. VC. Remember, this defines the Riemann tensor. What have I done? CD AB times VD, right? Okay. Now if we vary this equation, so let's, as usual, instead of starting with the commutator itself, let's just start with the product, and then we'll get the commutator by anti-symmetrizing in A and B. So we want to take the variation of this object. That's equal to, so it can vary between, it can change for two reasons, because this covariant derivative changes or this covariant derivative changes. So it'll have two terms. It'll have what I call the variation of the grad A, the covariant derivative, acting on grad B VC, and there'll be another term where it's the covariant derivative of the variant of the variation of grad B acting on BC, right? Okay. What is this? Now remember the rule. Remember the rule for how this difference of the covariant derivatives acts, which is the same as the rule for how the Christoffel symbol acts in a coordinate chart on a tensor, which in this case is a tensor with one covariant and one contravariant index. So first it acts on, say, the contravariant, say on the covariant index. So it's minus delta gamma. That's the tensor representing the variation. There needs to be an A here for the derivative. There needs to be a B for this index, which we're working with at the moment. And then a dummy index, let's call it M. What did I call it here? I called it D, dummy index D, okay, for a dummy index, grad D of VC, right? But that's only one term. There's this other index also, the contravariant index. So we have to have it acting on that as well. And so we'll get plus in this case, because it's a contravariant index, the variation in the connection, the tensor that represents that. Now we need a C here, we need a D here, and we need, as before, we need a B here. And we get that free index with the D.
We're still counting the first term, just the C derivative, right?
We're just doing the first. First I did the B, then I did the C. So now, what have I?
Should be CDA then on gamma?
C. It should be B. Oh, this should be. Wait, what's wrong? D.
Should the B be replaced by A?
Should the B be replaced by A? No, I'm doing. Oh, you're right. Absolutely, yeah. I left out. That's absolute, and I left out the B here. Yes. Yes. So it should be replaced by A and D, indeed, and B should be replaced by Z. Exactly. And this should have been still a D. Okay. And then finally, grad A. Now I have to do the same. Now I have to write down what I probably had written down before, which was delta gamma. We need a B here, a D here, a C here, B. We need a D on the V, and the whole thing to take the covariant derivative. Okay, so does that look right now? Good, okay. So now we're going to anti-symmetrize in A and B, right? Whereas this is symmetric in A and B, so we can drop that at this point, even though it's not really zero yet. But it won't contribute when we do the anti-symmetrization. And then we have to expand out this second term, or this last term. And so this last term, if we expand it out, is grad A variation of gamma CdB times VD plus variation of gamma CdB times grad A VD, right? Now, if I did it right, we should notice that this hold on. Yeah. We should notice that this and this is, yeah, so this, I see. So this, if you compare this term and this term, they both have the variation of gamma and a derivative of v. They both have c up here and d down here. The only difference is that one has a here and b here, and the other one has the b on the variation of the gamma and the a on the covariant derivative of v. So these two terms again, when we come to anti-symmetrize, they'll go away. So we'll be left only with one term. So I can say that it's, I'll put this symbol, meaning it's not literally equal, but it's equivalent to, in the sense that as soon as we do the anti-symmetrization, there'll be no difference. So the only term that survives is this last one here, which is the gradient of the variation of the covariant derivative, c dv, acting on v, right? So that's the answer, except that we have to anti-symmetrize. So the result, so the final result, so it was actually quite straightforward. And the final result is that the variation of the Riemann, well, we have to set this equal to, of course, what is this equal? Well, I have to anti-symmetrize first. Okay, so let me do that. So the variation of grad A, grad B acting on VC is equal to the anti-symmetrization with respect to A and B of grad A, right, delta gamma C dB. Okay. And there's no A or B in this B, so I can take it outside of the anti-symmetrization. But this is, of course, this was just the go back and look at the formula for the Riemann tensor, which I thought I wrote down somewhere. Did I? Well, if I didn't, this was the variation of R. I'm sure I wrote it down somewhere. Oh, here it is, yeah. So if we vary this, then we have to vary our CD, AB. And of course, we're not varying D. So we have those as equal, and therefore we can just cross off. V is a completely arbitrary vector. And so that's the formula for the variation of the Riemann tensor. So the variation, so just to write it again, the variation of R, C, D, A, B is equal to grad A. And I have to anti-symmetrize it in A and B. Okay, so that's the second main formula. I wanted to say something about it. It's sort of, again, it sort of falls into the category that the only thing it could have been, kind of thing, except modulo choices of signs and so on. So it had to be anti-symmetric in A and B. So we have to, that counts for the second term. It has to involve the variation of the connection because the Riemann tensor depends only on the connection. But the connection, of course, depends on the metric, but this definition of the Riemann tensor here doesn't see that fact. So all that can be involved is the variation of the connection, and that's defined, as we know, by some tensor with this index structure. So if you think about it, there's more or less, I think it's true to say, there's only one kind of combination that you could write down. If you were to put here an A and B, which we had such a term actually, it goes away in the anti-symmetrization. So the 1A has got to be here, 1 has got to be here, and that more or less pins everything down, except for the overall sign, which I would say is impossible to remember, but I mean, you have to come up with some set of conventions, and you can remember it. Hopefully, okay. So then the third thing we need, well, so now we have this. Now we can immediately get the variation of the. Let's take this and multiply it by the identity, or the Christoffel, the Kronecker symbol, if you like, which is this identity tensor, or whatever you like to call it, Christoffel tensor, acts as the identity when it's contracted with a vector or a covector. If we just apply that to this result, of course, contraction commutes with variation. So that tells us what the variation of the Ricci tensor is now. It's just the contraction. It's just this. We just need to contract on A and C. So we get grad A variation of gamma A dB minus grad B variation of gamma C. I'll switch them around, just who knows why, but I've switched them around anyway, so that, which is okay because gamma variation is symmetric. Okay, so this is the formula that follows immediately for the variation of the Ricci tensor. Now the two terms don't look the same anymore. In fact, it's not even obvious when you look at this that the right-hand side is symmetric. So we know this is symmetric, this is symmetric. So of course, this better be symmetric, but it's not evident from this formula. And the reason is that this formula doesn't know, the way we derived it, it doesn't know that this connection actually came from a metric. It could have been some more general connection, which wasn't derived, wasn't metric compatible. In other words, it wasn't coming from the equivalence principle. So there's no it can't be that this will always give us a metric answer, but we can do at least a consistency check. I mean, we know that it will be symmetric. So let's do some little consistency check on that. We can do that using something else, which again comes from the fact that parallel transport preserves length, which is another way of saying that we got it from the equivalence principle. And here's one check. Remember that the fact that remember when I talked about thinking of this Riemann tensor as a kind of curvature of a gauge, by analogy with gauge fields, a kind of curvature. We saw it, indeed, it represents the result of an infinitesimal parallel transport around the surface. The fact that it preserves lengths is this trace-free condition. So we can see what that implies. So we know that this is true. So let's take the variation of this fact. So I have to take. I hope the indices match. No, they don't. If I want it to match up with this, yeah, they do match. Okay. So if I want it to match up with this, I have to contract on C and D. So I'll get the left-hand side is the variation grad A variation of gamma. I have to contract C and D, B minus grad B variation of gamma C, C A. And we know that this is 0 because it's the variation of 0. And so so notice what's here is exactly the anti-symmetrization of this second term. So that implies, so I can just get rid of all this and just say that these are equal now. And that, well, that explicitly shows that these two terms are equal. Okay. However, it proves that they're equal, which we already knew anyway, because we knew that the right-hand side had to be symmetric. But again, it doesn't express the variation in some form that you actually see that it's equal, but it's another independent check that everything is well. So finally, so now we've taken the variation of the Riemann tensor, the Ricci tensor, and now we have to contract again. Now it's not so easy. We have to contract again and take the variation of the Ricci scalar. So we couldn't, of course, easily contract this with G, but that's not the whole answer because we have to, because the Ricci scalar involves both the metric. To go from the Riemann tensor to the Ricci tensor, you didn't need a metric. You just needed to contract a pair of indices. But to go from the Ricci tensor to the Ricci scalar, you do need the metric. And therefore, the variation of the Ricci scalar involves variation of the metric. And so that there's going to be two terms now, coming from the variation of the metric and plus coming the variation of the Ricci tensor. But it's important to understand what this means. This means you could read this two ways when I write variation of gamma AB. It could mean vary the metric and raise its indices raise the indices on the variation, or it could mean what it does mean, which is take the inverse metric and vary it. And those are not the same thing. So I'll put here parentheses just to indicate what it is. And so for that, we need another general rule, which I'll write here in the form that we need it, but it's actually completely general. So the claim is, see, there's no reason we couldn't stick with this, but in the end, when we want to get the field equations, we need to get some quantity multiplied by the variation of the metric equals 0, and then the variation of the metric is arbitrary, and that'll give us the field equations. But if we need to have the variation of the metric everywhere, or the variation of the inverse metric everywhere, and it's a little more convenient to have the variation of the metric everywhere. So therefore, I have to relate this variation of the inverse metric to the variation of the metric. Obviously, they're equivalent information because the two remain inverses of each other. If you know the variation of one, you know the variation of the other. And that's, again, a simple formula. But the form in which we need it is this. It's equal to minus the variation of GAB times RAB. Right? So what have I done here? I've taken all the upstairs indices and lowered them, and the downstairs indices and raised them. If that were the whole story, of course, I would just get the same answer. But it's not the same because here I'm varying the covariant metric and here I'm varying the contravariant or the inverse metric. And then you get a minus sign. So this is a completely general statement about any tensor, really. Or at least any symmetric tensor, so I don't worry about orders of indices. So if I contract this, so that's the rule. Perhaps it's well known. I don't know. Is it well known to everyone? Something like this? No. Okay, then I'll tell you how you can prove it. It's just a short proof. Just take the equation that but anyway, this is a nice form to remember the rule. So whenever you see the variation of the inverse metric, as long as it's contracted with something else so that there are no free indices left, you just swap the types of indices and you get a minus sign. So that allows you to convert the variation, the metric, inverse metric to the variation of the metric. You just start from the definition of the inverse metric. And you vary that equation. So, of course, the variation of the Kronecker tensor is 0. And so it just tells you that the variation of the inverse metric times, the variation of times GVC C plus GAV, variation of GVC. It tells you that these are equal, that this is equal to minus this. The sum of those is 0, right? And now just go and contract, play around. I mean, the next two steps are more or less trivial. Okay, and if you like, raise an index over, I mean, put this on the other side, and you'll get an expression for the inverse metric in terms of the metric variation, and then multiply it by r, and you'll see all the other g's cancel out, and you'll get this expression. You might have seen this in another form. Suppose I have an operator. Suppose I want the variation of M inverse. The general statement is that it's equal to, think of M as some operator or some matrix if you like. It's equal to minus M inverse variation of M times M inverse. You might have seen the rule in that form. Does that look more familiar? Yeah. Again, it follows from the same simple manipulation. Okay, so we have this, and so now we have everything we need to assemble to produce the variation of the Ricci scalar. And in fact, the variation of the integrand, which is r dv. So now we get the variation. We're interested in this term in the integral of r dv. So, and varying the integral is the same thing as varying the integrand. So we're not varying the region over which it's integrated. So we get, so from this, so now what have we got? From this, oh, I didn't write this down. So this is equal to, maybe I should write this down. Did I have it? It seems that I should write it down. So that's equal to minus delta GAV times RAV plus the same plus GAV. So we have to contract the variation in the Ricci tensor. So here we use D and B. So it amounts to contracting D and B. So what do we get? So we get grad A, variation of gamma A, B. Since this is symmetric, I can just call it BB, GBB. Now we have to contract D and B minus, now I have to do GBD, let's say, variation of gamma C. Oops, I left out gradient B, variation of gamma GC. D, okay. And this thing, now, this term I can also, this is just a covariant derivative, so of course I can pull the G inside because covariant derivative of the metric is 0, therefore the covariant derivative of the inverse metric is also 0, so that becomes the divergence of GBD, variation of gamma CCD. Something like that. Okay. So it's equal to minus variation of GAB times RAB plus, let me just pull out an overall divergence. And now it's the variation of gamma of A, B, B, G, B, B minus, so I have to swap alpha, I have to swap the dummy index A for B now, and so I'll get G, A, D, or I can even call it GAA, variation of gamma CCA. I hope that's legible. Anyway, it's not too important what this term is at this point because we're about to drop it. But when we come to consider more general things, especially definitions of energy in gravity, conserved quantities, then this surface term becomes important. And it's important for other purposes too. So it's good to know what it is. Okay, so that's the variation of that. So then what have we found? So now we have the variation of this integrand, r dv. It's the variation of r times dv. So we just found the variation of r. So it's minus delta g ab r upstairs ab times dv plus this other stuff, which I'll put off at the end. But we also had the term, first let's get the term that came from varying dv. So we have to write for that plus r. And for the variation of dv, I had it somewhere up there. Maybe it got covered. Oh, there it is. Yeah. So it's that one up there. It's just above the lower blackboard. So that's r times 1/2 dv times gab, variation of gab. And then finally this other term, which is grad A of a whole bunch of stuff, which is right above, which I won't write again, but has a single index, free index A here on it. Okay. So we're more or less done. So except we have to give a name. So we have to do a little bit more with this combination here. We want to pull out the variation of g, and so we find the variation. Let me restore the integral sign now. So it's the integral variation of gab from these first two terms. And what multiplies it is minus rab plus 1/2 gab times r, right? And then there's another term, which is the integral of this thing here, also integrated over the region in question. And we also need before the other one, let me say, so this is given a name, since this is the thing which multiplies the variation in g. It's given a name which is GAB, except with a minus sign. So GAB is defined then, but it's just a notation for this combination that appears here, which is RAB minus 1/2 GAB times the trace of RAB. So we've taken out the trace of R, but we haven't taken it out fully. In fact, if you work out in 4 dimensions, if you think about what the trace of capital G, called the Einstein tensor, if you think of what its trace is, you'll get R, but then you'll have minus 1/2. But when you contract the GAB with itself, you'll get 4, the dimension of the space-time, right? When you contract the metric with itself, you always just get the dimension of the space-time because it's equivalent. If it's not familiar, do a little calculation. GAB. You can think of this second GAB as lowering the index B, and so we get sort of GA A. But of course, lowering the index, I mean, this combination is also, by definition, since we're multiplying the inverse matrix by the matrix, it's the Kronecker symbol, so that GAA is also delta AA. It's the identity. And of course, when you take the trace of the identity, you always just get the dimension of the vector space in which it's acting. So it's equal to 4 in 4D. So this would give a 4 minus with a half, it gives a minus 2. So actually, it turns out that the trace of GAB is minus the trace of the Ricci tensor, which I'm only mentioning that because people often call it the trace reversed Ricci tensor, and that's what they mean. That's all they mean. You add that multiple of the trace, that instead of making the trace 0, makes it minus what it was. Okay, so anyway, this is that's the main result. And then, so if we had no cosmological constant and no matter terms, only gravity, then the field equations, which would be like the analog of the source-free Maxwell equations, they would just say that this Einstein tensor vanishes. And since we saw that its trace is non-zero, that implies that also the Ricci scalar vanishes. And then because the Ricci scalar vanishes, and the Einstein tensor vanishes, therefore the Ricci tensor must vanish. And so in the case of no cosmological constant and no sources, the field equations of gravity are just that the Ricci tensor should vanish. So sometimes you call it Ricci flat in the case. So if lambda equals 0 and matter equals 0, so then it implies Ricci flat. In other words, not the Riemann tensor itself is 0, but its contraction that gives the Ricci tensor a 0. But in general, we have both matter and cosmological constant. So, or in the real world also, we have both matter and the cosmological, presumably a cosmological constant. And so we need to add that term. So the variation, so actually we need also to put a 1/2 here, because that's what was actually in the action. So we get plus a 1/2 here. And then we need to vary integral lambda dv, what was it, minus lambda times the variation of dv, which is minus lambda times the integral of 1/2 dv times GAB, variation of the GAB. So when you put those together, the variation of the gravitational action is equal to these two terms, 1/2 minus 1/2. Oh, I've also, for the moment, for convenience, set the coupling constant. Well, no, let me keep it here, just for symmetry. Okay, so 1/2 kappa, so I won't set it to 1 yet. It's equal to minus 1/2 kappa times, notice, by the way, here the same rule works nicely. If you see a contraction of two completely symmetric things, you see a 1/2 with it. But this maybe doesn't work. Yeah, that's right. And so then we have also plus, minus, I should say, this thing, which is another 1/2 GAB, variation of little GAB, dV. Okay. Or just, did I leave something? And the lambda itself, exactly. Okay. And so if I pull out the delta, if I now plus this other term, which we have to still worry about, and it's maybe a 1/2, depending on what you mean by that parenthesis thing. So now, to get the field equations, we now just let delta lambda be arbitrary. So the whole thing takes the form of the integral 1/2. It takes the form of the integral dv, 1/2 variation of GAB, and then whatever is multiplying it will be the field equations. So it's minus 1/kappa GAB minus lambda GAB. Okay? Plus this other term still. So we see what the field equations are. At least if we can neglect this other term, we see what the field equations are, and they are that 1 over kappa, or let me just multiply, so I can obviously change the sign, and let me, for some reason or other I've done in my modes, multiply through by kappa. So it says GAB plus lambda kappa GAB equals 0. So these are the, this is if there's no matter. So this is still the source free. This is source free. So those are the Einstein equations in the presence of cosmological constant, but still no matter. Now why did I keep putting off explaining why we have to, why we can neglect this? And that's because we haven't really developed a nice machinery to prove that in a nice way. So I'll prove it. So just like this thing, this can be easily proved, but we hadn't proved it. And this one, it's a little harder to prove it. So I'll put that off and come back. So I claim that whenever, however, so there's a general fact, that's the important thing. We'll have to come back and justify it, at least in this particular case. But there's a general fact which says that that if I have anything of the form integral of d of dA, anything, let's call it WA. So it looks like a divergence, but it's a covariant divergence. And I integrate it over any region. That's equal to some sort of surface integral over the region. So it looks exactly like the formula you know from flat space. That's the nice thing about it. If you're careful to keep the indices in the right place, and if you're capable to define this ds, the surface element, in the right way. But it's basically what you're already familiar with. It's sort of the unit normal to the surface times the measure of the surface, at least in the case where the surface is time-like or space-like. When the surface is null, it has a slightly different expression. But all that stuff is important when you have to worry about the surface term. But since in this case we're only doing variations of compact support, the integrand, this W, of course, depended on the variations. And so it's under here somewhere. Here it's this expression. That's that W. And so the variations vanish on the surface, then we don't have to worry about that term. The important thing is that integral of a total divergence always converts into a surface integral, and that remains true in curved space. And as I say, we'll come back in a second. Although it's true in general, we'll come back in a second and prove it. Well, maybe we might actually just prove it in general, actually, but we'll prove it in this particular case anyway. Okay, so now what about, so that's pure gravity. So let me make a couple of comments. So these equations are not easy to solve. You need, in general, if you write them out in components, they're in a coordinate chart, they're very complicated equations. So it's nice to solve them in a few cases where you can. Of course, the important one will be spherical symmetry, which I guess we'll do next time, which will lead to the Schwarzschild metric. But we can completely solve these in 1, 2, and 3 dimensions. So just for fun, let's do those, yeah.
When we were reviewing the action of the test particle, there was a case where we don't have the variation fixed at the endpoint, so we got some new information.
Absolutely, yeah.
What happens when we do that?
Exactly the same thing. So we get new information. So if you were to, but that new information was used in 2 ways, or could be used in 2 ways. We actually used it to derive conservation laws, right? And so exactly the same kind of thing happens in curved space, but you have to be much more careful about what kind of symmetries you're talking about. And if you go back to that discussion we had before, it's really symmetries with respect to some sort of ambient metric at infinity. So when you have an asymptotically flat space-time, then you can sort of think of moving the whole system with respect to infinity, and you still have the whole Poincare group there in that way as a kind of symmetry. And so you can exactly derive, in a strict analog almost, well, I'd say almost a strict analog of what we did for the particle. You can do it for the field, and it gives you the conserved quantities associated with gravity. So that's one way in which it can be used. And then the other way it's used, if you want to write a Hamiltonian or a canonical formulation of this, if you want to identify the conjugate momenta of the sort of configuration variables. Remember, what we found was that the integral, that the sort of, the variation of the action was equal to some term, sort of d lambda, which vanished when the equations of motion were satisfied, plus a sort of p dq type term. And then this goes to zero when the equations of motion are satisfied. So if you vary about a solution of the equations of motion, then remember the variation of the action gives you the definition of the momentum. And we didn't do this. We used it for interpreting the conserved quantities, but which was form momentum in that case, basically. Or in the case where you had only a time-like killing vector, it was the energy associated with the time-like killing vector. But there's another way in which it gets used, which is these are the conjugate momenta. So in a quantum theory, one would imagine something like, you'd imagine that they're conjugate in some way. Or in the classical Hamiltonian formulation, which really you can do, unlike the quantum one, in the case of gravity, which no one really knows how to make sense of completely yet. But in the classical case, it's the Poisson bracket, not the so-called Poisson bracket, not the commutator. And then that gives you a set of canonical variables in which you can write down a Hamiltonian and then the field equations. There's a whole, the Hamilton's equations of motion. And there's a whole long story that goes with it. And that's one way of formulating gravity, in which you think of it. You think of the metric as the four-dimensional metric. You think of it as a kind of three-dimensional metric evolving in time. The story gets more complicated because gravity is really a gauge theory in the sense that it has diffeomorphism invariance, and so the phase space is more complicated. It has constraints. Anyway, there's a lot of, but that's the other. It all comes. The very first step is to identify what are the conjugate momenta to these would then be the spatial metric. And again, you do that precisely by finding the variation by the surface term. Right? You do the field theoretic analog of this equation that we wrote down for the particle, and it'll give you the conjugate momenta. So indeed, the boundary term, if you wanted to ask what is the boundary term, just for future reference, for this kind of reasons we just went over, the boundary term, which we're about to drop, was 1 over 2. It came really from, remember, of course, like it always does, from an integration by parts. So from bearing the term cosmological constant term, we didn't have to do an integration by parts. The integration by parts was precisely this, converting the divergence into a surface integral. So we'll only get a contribution from that, and I'm just copying, I hope, from what I have over there, except I think I've changed the minus G. What have I done here? C, yeah. Can't even read this, but this is what it should be. Okay, so that's the boundary term that we dropped. Now it looks like a total divergence, but I claim we can convert it into a boundary term. And so when we convert it into a boundary term, it'll become this will get converted into a surface element like that. And it'll now be over the boundary of the region kappa. That's the boundary term. Okay, so that's the derivation. We have only one. Oh yeah, I wanted to solve it. So there's one big thing we have to do more to make it more complete physically, which is we have to add matter. And aside from that, we have to go back and justify a couple of steps. Well, really just one step now. This one we justified in the, oh no, we have to justify the two steps. This one, I'm always losing it, but this one, only in some sense of losing it, but we have to justify this one and the integration by parts. But before doing that, since it's fun to solve these in low dimension where everything is so simple, let's do that quickly. So let's look at D, or N, I'll call it, the dimension is equal to 1, 2, and 3. So it's probably has some significance that 4 is the first hard dimension, and we live in 4 dimensions. But so 1 is, of course, trivial. And in the case of one dimension, you're just dealing with a one-dimensional Lorentzian manifold, which is just like time. There can be no notion of curvature, intrinsic curvature, since there's no non-trivial loops to go around. So of course, you can only go forward and back. But if you go along a loop that's like this, obviously nothing changes. So on many grounds, we're not going to get anything too interesting in one dimension, namely the Ricci tensor is Ricci scalar is exactly 0, identically 0. So when you vary it, you'll still get 0. So the only variation will come in one dimension will come from, where was our, so the Einstein tensor will be exactly 0. And so GAB, which is just G00 now, but I'll call it just GAB, is equal to 0. And so our equation, which was GAB plus lambda times, this was really 1 over kappa, lambda times little GAB, that would imply that GAB, inverse metric, I guess, would be 0. So that's not very, whatever it is, it doesn't represent a space-time. No time, there's not even a metric now because you can't invert 0. So anyway, so it's just a nonsense, as you might expect. In the case, but I guess there were two possibilities. Either you would get, in fact, there are two possibilities. Either you get a nonsense if lambda is non-zero. If lambda is non-zero, you get a nonsense. If lambda is 0, then it's another sort of nonsense, which is that anything is a solution, right? But of course, so GAB in that case is arbitrary because the action you started with was 0 when lambda was 0, so you're not going to get any useful equation. So actually, I called it a nonsense, but in a sense, it's not. In a sense, it's quite reasonable. It's just some flat one-dimensional space-time, if you regard that as being reasonable. No space, just time. Whatever you may think about it, it's quite trivial. In the case of 2 dimensions, it's more interesting. In the case of 2 dimensions, we have to go back and do a little calculation. Maybe for all dimensions, it'll be useful to do this. So what is the trace of GAB? So I mentioned that before. So we look at its definition. Look at its definition, which I can't see there, but it had r minus 1/2, so it's minus n over 2r. So the trace of the Einstein tensor is 1 minus n over 2 times r. So in the special case where n equals 2, this is 0. And in fact, so it's supposed to be obvious, but
Isn't GAB supposed to be symmetric?
it is symmetric, right? And in fact, it actually vanishes. But I'm trying to see why. That should be obvious, but I'm not seeing the... Oh, maybe it makes a little work. So it is symmetric, yes. So what? Oh, yeah. So in fact, what's not entirely obvious here, but so this is in the case of 2D, is that the Einstein tensor itself is 0. You can make it very plausible by counting independent components. If you count independent components of the Riemann tensor, so I'll just make it plausible now because there's no time to do the proof. But if you count the independent components of the Riemann tensor, it has, in 2 dimensions, it has just one component, one independent component. In 1 dimension, it has none. It's 0, right? In 2 dimensions, it has one independent component. And so the trace, so there should only sort of be one component. The trace, is that a good argument? As I say it doesn't sound all that convincing. But anyway, it is a fact. I'm sure there's a better way of thinking about it, which I'm not getting at the moment. But it is a fact that the 2-dimensional Einstein tensor vanishes identically. It's also related, I mean, the nice way of remembering it is related to so-called the Gauss-Bonnet theorem, which tells you that the action, the integrated scalar curvature, depends only on the topology. But to prove that theorem, really, you have to go the other way and show that the Einstein tensor vanishes. Oh, this won't be quite obvious because, yeah, show the Einstein tensor. If you can show the Einstein tensor vanishes, then since the Einstein tensor gave us the variation of the action, then you're saying the action doesn't vary when you vary the metric. So what can it depend on? Only on the topology of the space on which you're integrating. Anyway, so in that case, it vanishes. So in 2D, the equations look like this: GAB plus kappa lambda little metric GAB equals 0. So again, it's a little bit like we saw before. And this is actually 0 now. So it's the same equation we had before. So the answer is the same, but it's a little more interesting. If lambda is non-zero, there's no solution at all, no physically sensible solution. On the other hand, if lambda is 0, so lambda is not equal to 0, implies no solution. If lambda is 0, it's exactly the same. So an arbitrary solution. In other words, any metric whatsoever is a solution, classically speaking. And it turns out that all the interest, so again, it's nothing interesting, at least from a classical point of view. It turns out that in the quantum version of it, some particular quantum version of it, that you do have some sort of non-trivial dynamics, but it's all coming from the path integral and the fact that you have to integrate. It's coming from the fact that there's more to a quantum theory than just the classical approximation to the theory. In this case, the classical approximation gives you nothing, but the so-called integration measure for the path integral gives you the whole story. Anyway, at a classical level, which is where we are, there's nothing interesting. So the first really interesting case is where n equals 3, and so I wasn't planning to do, so let me just tell you what the results. Why have I got this here? Okay, so in n equals 3, what happens is that if, let's take the simplest case where lambda equals 0. In that case, what it turns out that it implies, as we saw before, that the Ricci tensor equals 0, and that implies in 3 dimensions, again, if you count independent components, it tells you that, I'm just thinking about something else. Yeah, I remembered how this other argument was supposed to go. Okay, so anyway, in 3 dimensions, it tells you that the vanishing of the Ricci tensor implies the vanishing of the Riemann tensor. Again, you can make it plausible by counting components, and you see that there are no more independent components of this, given the symmetries, than this in 3 dimensions. And there are 6 of these, because it's just an arbitrary symmetric matrix. And so basically you get a flat space-time, somewhat like 1 dimension, I suppose, but it's more interesting to have a flat space-time in 3 dimensions than in 1 dimension. Yes, the argument here was that if we take so I'm going back to the 2 dimension, which I didn't give the argument very well. So if we go back, if we take the trace of the Einstein tensor, we put here n equals 1, we get it's up to some non-zero multiple. It's the Ricci scalar. So if the Einstein tensor is to vanish, I mean, if it's if we set lambda equals 0, then the Einstein tensor is supposed to vanish, and then that means its trace that means the Ricci scalar must vanish. And then by counting, as I said, Riemann has only 1 independent component, which we can identify with the Ricci scalar. And so if the Ricci scalar vanishes, then the Riemann tensor must also vanish. So in the case where, I think I said it again. What am I talking? What dimension were we talking about here? 2. So everything that I said was for 1. Okay. So for n equals 2, this is 0, so we don't get that argument. So I'm still not giving the argument. Maybe there is no entirely simple argument for why. If there is, I'm not remembering it. Okay. So now henceforth we can assume that the dimension is greater than or equal to 3. And in fact, of course, we might as well assume it's 4. Let me go back and do the other important things, which is to add matter. I want to make one other remark. Where do we have all these? Here it is, yeah. So one other remark I wanted to make is that in 4 dimensions, we saw that if lambda is equal to 0, it has to be Ricci flat. By taking the trace of the Einstein equations, you will find that in 4 dimensions, if lambda is not 0, then the Ricci tensor has to be a multiple. It has to be proportional to lambda times the metric. It follows trivially. Just because we're running out of time, I won't do it. But it follows trivially just by taking the trace of this equation and relating the trace of the Einstein tensor to the Ricci scalar in the way that is written somewhere. Again, I've lost it, but lost where I wrote it. But it was it's over there. Yeah. By using this relationship and taking the trace of the Einstein equations, you'll see that the Ricci tensor has to be a multiple of the metric. those are sometimes called Einstein spaces. That is, ones in which they're not Ricci flat, but they're almost as flat as it could be when the cosmological constant is non-zero. See, when the cosmological constant is non-zero, well, let's take the trace of this just to see. So we found the Einstein trace of the Einstein tensor was, take the trace, what did we find? 1 minus n over 2, which is in 4 dimensions, okay, times the Ricci scalar plus lambda kappa times the trace of GAV, which is n. That has to equal 0. And so we get some relationship between between lambda. We can solve this for lambda we can solve this for lambda in terms of the Ricci scalar. We can solve it, sorry, for the, as long as n is not 2, we can solve this for the Ricci scalar in terms of lambda, okay, and the dimension. So the Ricci scalar is completely determined in the case where lambda is not 0, is proportional to lambda. Then you plug that in to this definition of the Einstein tensor, and you'll get just some multiple of the metric here and some multiple of the metric here, and what's left over will be the Ricci tensor. So the result will be that the Ricci tensor is a multiple of the metric. That was the other remark. Okay, so now let's do the more important thing physically, which is to put in matter. So how do we put in matter? Well, we'll assume that there's an action for it too. And we'll assume, moreover, assume that it depends on, it's some function of the matter fields, whatever they may be. So I'll just call them phi in some generic way. That was the Newtonian potential. We'll call it just phi, the matter fields, and the metric, of course. As you know, you basically can't, if you think of all the different field equations you've ever seen, you probably never saw one for any matter field that you, or particle that you can write down without involving the metric. So in general, it will depend, but in general, it won't depend on derivatives of the metric, unlike the gravitational action, which does. Oh, that reminds me, there was one comment I wanted to make, which I forgot to make, which is that when we did this whole derivation of the Einstein equations, we never actually had to go back explicitly and work out what the variation of the action was in terms of the metric. It sufficed to work with the variation of the Christoffel symbol or of the covariant derivative. So that's just a convenience, but of course, it doesn't mean that the variation of the metric is not involved in it. Obviously, it is. I mean, it's kind of interesting, though, that you didn't ever need to explicitly see what these variations were. But if you had written it out in terms of the metric explicitly, you would have seen, of course, that you had second derivatives of the metric coming in. And you might have wondered why you got only second derivatives of the metric coming in, even though we started with we started with a Lagrangian, which had second derivatives. So normally when you start with a Lagrangian that has second derivatives and you vary it, you generally get fourth order field equations. That's because generally the second derivatives would occur in some, for example, squared or some combination, so that when you did the integration by parts, you would throw two derivatives onto the two that are already there and get 4. But there's something special about which we never pointed out too much. There's something special about the Ricci scalar, which is that although it does involve second derivatives of the metric, it only involves them linearly, and then some other metrics to make other things involving the metric to make contractions, and maybe some other terms that involve involve Christoffel symbols. Now I'm thinking in a coordinate chart that involve just first derivative squared. When you vary such a thing, then you only get second derivatives, right? Because either you vary this or you vary this, But if you vary this, then by doing 2 integrations by parts, you only still get 2 derivatives. And here you do 1 integration by parts. Anyway, so it's an important feature of the Einstein equations that they are, in fact, second order, which I talked about the other day. But now we see explicitly that they are second order in the metric. Okay, so we'll assume that the matter has this form, and then we give a definition where we vary the metric now, just as before, and we hold the matter fields fixed. There's a small caveat there for spinors, but let me ignore it. So basically, vary the metric and hold the matter fields fixed, and find the variational derivative by the usual way, convert the total divergences to 0, and you'll always end up with an expression of this form. Right? Do a variation of compact support as before. And then we define, so this is the other important equation. We actually define the stress energy tensor of matter to be this variational derivative. That's actually the nicest definition of the stress energy tensor for matter. It's even nicer than the one that we could have given using the Noether theorem, because it fits so nicely into the Einstein equation. Then it's another story why those 2 definitions are equivalent. The one that came from the sort of Noether kind of conservation laws approach and this variational derivative approach. There's actually, I just won't say it because we're really running out of time, but there's a very close analogy of this in the case of Maxwell's equations. Conservation of charge follows twice. Well, let's finish this, and then I'll say the analogy. So this is defined, the definition of TAB, which we call the stress energy tensor of matter. Now, if you compare this, so that just produces another term. If we now say that the variation of S gravity plus S matter is 0 when we have matter, we'll just get what was the variational derivative with respect to the metric of the gravity term. So there's this overall factor of 1/2 variation of GAB. So we'll get integral of 1/2 variation of GAB, and then we'll get minus capital GAB over kappa. Minus lambda little g AB, and then by definition of the stress energy tensor of matter plus TAB, that whole thing will have to equal 0. And so if we bring the Einstein tensor to the right-hand side or the left-hand side, whatever that is, then we say that equals TAB minus lambda times little GAB. So that's the full Einstein equations, including matter. So there's a few comments that could be made, but the most important one is not a comment, it's the conservation law. So the crucial thing is, I was going to make some comments about thinking the way cosmologists do about the lambda term as a kind of fluid, but beyond saying that, there's no time to explain it more. But the conservation law is a crucial thing. So now remember that we had proven that grad A GAB equals 0, okay, just as an identity for the Einstein tensor. I think last time we proved it from the Bianchi identities, or not last time, I think, time before, anyway. In the recent past, we proved it from the Bianchi identities. And if we look at this equation, what does it? Let's apply this to this equation. What does it tell us? It tells us that grad A GA. It tells us that which is equal to 0 of the left-hand side is equal to grad A TAB. Oh, by the way, this is the definition of TAB, and it's also implicit in this that we define we define this to be symmetric. Right? In other words, I could put in any antisymmetric thing here and it wouldn't change the contraction with the variation of G. So it's, of course, we define TAB to be symmetric. And then this equation uniquely determines it. Then we get minus lambda. Well, we get the variation, we get gradient of G. But of course, that's 0 because the covariant derivative of G is 0. And so the result is, and lambda is a constant, so we don't have to take its derivative. It's an interesting story. What if you tried to make it non-constant? You'll see you'll be forced that it'll be constant in the end anyway. But for us, it's just a parameter at the moment, a parameter in the action. And so we learn this, grad A TAB equals 0. So the divergence on one index of the stress energy tensor is 0. So this is the called conservation. It's the generalization to curved space of the flat space law, which looks exactly like this. If you're familiar with it, hopefully you're somewhat familiar with it. In flat space, you write, it's the same thing, but I'll write it as a partial derivative, just to emphasize that it's flat space. So this is in Minkowski space, let's say. Maybe you're familiar with the fact that this represents conservation of momentum and energy. You interpret certain terms of this as energy density, another term as energy flux or matter flux, another term as momentum density, another term as stresses, and so on. And this expresses conservation. In a continuum theory, this expresses the conservation of both energy and momentum, the local conservation of both energy and momentum. If you're not familiar with it, then this will have less meaning to you. But the important thing to notice is that it's not a conservation law in the same form. This one, in flat space, you can integrate this equation over a surface, and it tells you that the total energy and momentum defined on any hypersurface is independent of where that hypersurface is. In other words, it's a conservation law. This equation doesn't tell it to you. It only tells you in the presence of a killing vector, which is quite analogous to what we saw in the case of a particle. So there's no conservation law for matter alone in curved space, in the case of general relativity, be it particulate matter or be it a field. But we do get this. This is generally known as conservation law. And so now I just have to come back and anyway. So this is sort of the starting point for all future. Not this one. This one. Didn't we write down the full Einstein equation? Yeah, this one here is the starting point for all future developments, at least at the classical level. And then, of course, the trick is to know what is this TAB for any particular form of matter. So that's it, except for these two proofs. So let me do, yeah, was there a question?
For the three-dimensional case, we discussed when lambda was 0, but we didn't talk about when lambda was not 0.
Oh, yes, I ignored it. I skipped over it, absolutely, yeah. You'll get an equation, yeah, you'll get an equation like we had here. I had not actually planned to do the three-dimensional case to save time, but then I got somehow, I sucked myself into doing it. But you'll get an equation like this in 3 dimensions. And so instead of flat space being the only solution, it'll be a portion of, depending on the sign of lambda, it'll be a portion of a kind of positively curved, as it's called, which is like de Sitter, as it's called, or it'll be a portion of anti-de Sitter. Ran away. So let me do the more important. So there are 2 ones to do. One is we need to come back and prove and justify the statement that the variation of dV is equal to dV itself times 1/2 GAB times variation of GAB. I don't have a nice way of proving this. The nicest way that I know is to use, first of all, yeah, I just don't know a nice way to prove it, but there's a simple way to think about it, is that this variation of the metric represents a kind of distortion of the space, and this is just the trace of that distortion. So if you think about simple cases, like if you expand a little bit in this direction, contract in this direction, and so on, you'll see, and that's it, because you can always diagonalize a symmetric matrix, you can always bring it to that situation. If you think about it, you'll see that that's a natural equation. If you actually want to prove it by a formula, then you have to go back to it really reduces to the question, what's the variation of this square root of minus g? And that reduces to the question, what's the variation of the determinant of GAB? Obviously, once you can do this, you can get the square root. And so then you need a nice formula for the variation of the determinant. And I don't know a nice way. I know one nice way of doing it, which is to write the determinant as an epsilon, as a couple of epsilon symbols, and a bunch of, in this case, 4 copies of the metric. And vary this. If you vary this, you'll get one term coming in, which will be, for example, this one. And if you take out if you take that, pull that out, you can convince yourself that what's left is actually the inverse metric multiplied by the determinant. These are kind of the cofactors or something like that. And so the formula pops out, which is that what the formula actually is that the variation of the determinant is equal to the determinant itself times GAB times the variation of GAB. So if you can prove this, then you can trivially prove this other one just by taking the square root. But I don't know a really simple, nice way of proving this other than through that. The other way is to say that the determinant of a matrix, that the log of the determinant is equal to the trace of the log of the matrix. But this is only in quotes because the log doesn't always exist. Anyway, if you believe this and you believe that you can take the inverse under the trace, which you have to justify also, then you can also prove it from this. If you take the variation of this left-hand side, then you get the trace. Now I want to vary the log of the metric, so naively that's 1 over the metric times the variation of the metric, right? And that's the formula that we see here. The inverse metric times the metric, and then traced. So one is for multiplying the two matrices, and the other is for taking the trace. Anyway, there's many ways of proving it. So the other one, but you can probably convince yourself in many ways that it's true. So the very last thing I want to do is to prove this other thing, which is much less obvious, much more subtle, which is, well, I stated it before, that if I take any vector, its covariant derivative integrated over some region, I get a boundary integral. I won't prove the whole thing, but I'll prove something, what we need in a particular coordinate chart. The reason I have to do the coordinate chart again is because we haven't studied integration in a more general framework. So, and therefore we don't know how to work with this dv. So, but if we go in a chart now, then what will this become? This will become gradient A times root minus g times d4 x. I'll do it in 4 dimensions. But now the crucial thing is that I claim that the root minus g, so I claim that the root minus g times the gradient, now I'm doing it in a chart, so I'll use these Greek indices, A alpha. I claim that this is equal, I can convert, by bringing the square root of minus g inside the derivative, I can convert it into a an ordinary derivative in the chart. That's the key thing from the point of view of the chart. So let's check, if we check this, if that's true, then I'm done, right? Because then I bring this inside the chart, inside the derivative. It becomes partial alpha A alpha root minus g d4x. But now you can forget that you're in curved space. This just looks exactly like the divergence formula that you already know in flat space. We're working in a coordinate system. And so so now we do a sort of flat space, sort of an M, sort of, just call it flat. It's really not so much flat, it's just it's something we do in a coordinate system. And then this will just become A alpha times root minus g times some sort of thing, which I'll give a name d sigma alpha, which is the thing that looks like the surface element in the coordinate system. So, it looks like the normal coordinate area, blah, 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 blah. So all I've done is I've used Gauss's law for the coordinate system, or Stokes' theorem, or whatever it's called, Gauss, Stokes, those laws to convert a total divergence into a surface integral. So the key thing is just to prove, if I prove this, then I can always convert the total divergence into a surface integral. So the last thing we need to do is check, is this true? And then it becomes a kind of non-illuminating calculation, but let's check it in the coordinate system. So what was this covariant derivative? Remember, it was partial. I'll drop the parentheses now just to save time. It's that, but then we have the correction from the Christoffel symbol, which is alpha, alpha, beta, A beta. The question is, am I right to say that this is equal to just this coordinate derivative? Oops. So let me expand. So is it equal to this? So on the left-hand side, so what's on the right-hand side? We have partial alpha root minus g times A alpha plus root minus g times partial alpha A alpha. And the question is whether that's equal to this term here plus this term here, right? This term here, involving the coordinate divergence, it's crazy. It is there. This term here is just the same as this term here. So it all reduces to the question whether and then there's an A here. So it reduces to the question whether the square root of minus g times gamma alpha alpha beta A beta is equal to this thing here, partial alpha the square root of minus g times A alpha. And let me change it to beta. Okay. A was just an arbitrary vector field. So it reduces to the question, is it true that the gradient of the square root of minus g is equal to minus g itself times the contraction, sort of the trace of the Christoffel symbol. This is all in a coordinate chart. So that's all. This you just have to check. I won't go through it. It's just, we had this formula involving the Christoffel symbol, involving derivatives of g. For this, you have to plug in what we already know. This is asking you to find this. This is a kind of derivative, therefore it's a kind of variation of the square root of minus g. Therefore, gives it gives precisely expression like the square root of minus g times GAB, or alpha beta, I should say, variation of g alpha beta, and I think a 1/2. So that we have to check whether that combination of derivatives of the metric, I'm messing this up. Let's call this mu nu, partial beta. We want partial beta of the root minus g. The question is whether that combination of partial derivatives is exactly equal to the combination of partial derivatives from contracting this. And there's just 3 terms, but it's getting so late I won't write the 3 terms out. But you can check it for yourself. And the result is that they're equal. So this is a kind of messy, not very informative way, but it does prove that you can always convert a covariant divergence, total divergence, into a surface integral. That's what we used in deriving the Einstein equations. So that seems a good place to stop. So the next semester, for those who are here, we can start with the Einstein equations and apply them to derive the, first of all, the Schwarzschild metric.